Hello everyone, welcome back in the next video in this series of linear algebra question which are asked in the GATE examination in the previous year. So let's start this video with first question. Okay, question 1 says consider a matrix A. We have given a matrix A which is a 2 cross 2 matrix and a vector x in this form of x1 and x2. The number of distinct real values of k for which the equation ax equal to 0 has infinitely many solutions is. They're asking about the number of distinct eigenvalue this variable k can take in such a way that this ax equal to 0 system of equation has infinitely many solutions. Now first of all, look at this system ax equal to 0. It's represent a homogeneous system of equation because the right hand side here is 0 vector and here this a is nothing but our coefficient matrix and this x is nothing but this vector in terms of this x1 and x2, and now the system is homogeneous. So now the homogeneous system is always consistent, so I can say let's first of all form the homogeneous equation with the coefficient matrix. The coefficient matrix is this one which has value k, 2k, k square minus k and k square, and we have to multiply this with this vector x1 and x2, and on the right hand side we have given a 0 vector, so let's write it as in this form. So now this system is nothing but a homogeneous system of linear equation. So now the homogeneous system is always consistent and it has a trivial solution for any case. It's mean if the all the values here this x1 x2 and up to xn, let's put it here, if this x1 x2 and up to whatever number of unknown there may be, let's call xn, if this all variable take the value as 0, then the left hand side of this equation is also 0 and we have already 0 on the right hand side. So this condition, so this equation is satisfied for this values. It's mean this homogeneous system is always consistent. So now they are asking about the infinitely many solution. So now for the any system of linear equation we have one concept about the determinant of this coefficient matrix. So now let's this matrix we have called as A, this is x and this is 0. So now let's find the determinant of this matrix A. So I can say if the determinant of this matrix A, it has two possibility, either the determinant is 0 or non-zero. If the determinant is non-zero for any general system of equation, then I can say the all the rows or all the columns in this matrix A are linearly independent. Then I am getting determinant as non-zero. Then the system has unique solution. System has unique solution for this condition. Or in the other word, this matrix A has full rank. Then the determinant is non-zero. So now if this and the second condition is there, if the determinant of coefficient matrix here is 0, then again the two possibilities are there for this condition. And what are those? Let's put it here. The two conditions says if the determinant of any coefficient matrix is 0, then the first possibility is that the system has no solution, or in the other words system is inconsistent. So let's write it here, no solution. So this is the one possibility if the coefficient matrix here has the determinant as 0 for any general system of equation, not necessarily homogeneous, it's maybe non-homogeneous also. So now the second condition is nothing but infinitely many solution, infinitely many solution. So now here it is given that the system is homogeneous. So system here this possibility with this no solution is not there for the homogeneous system of equation because the system is always consistent. So this possibility is cancel out for the homogeneous system of equation. So now if the determinant equal to 0 of any coefficient matrix in the homogeneous system of equation, then the only the remaining possibility is this one. The system has infinitely many solution. So now simply we have to find the determinant of this matrix A and equate equal to 0 in order this system has infinitely many solution. in the question it is given that this ax equal to 0 system must has infinitely many solutions. So simply we have to find the determinant of this a and equate equal to 0. So now let's do it here. So I can say the determinant of a, we have to equate equal to 0 to get the infinitely many solution. So now simply here this matrix A is 2 cross 2, so it is easier to find the determinant of such matrix. So now here we can say k to the third power minus 2k multiply with this bracket which is k square minus k, and we have to equate equal to 0. So now let's further simplify it. So here I can say 2k cube minus minus will be plus 2k square, and already we have 0 on the right hand side. So I can say it is nothing but equal to 2k square minus k cube and equal to 0. So I can take k square common. So again it will reduce to k square multiplied with 2k, sorry 2 minus k and equal to 0. So I can find the root of this equation. So you can say the value of k is 0. This is the first root, and the second root is also 0, and the third root is nothing but plus 2. So now here this variable k can take any value from those four number, but here this 0 is repeating twice. So I can say k can have two values, either 0 or 2. So that is what they are asking in the question. They are asking about the number of distinct real values for k. Here this k, and we have find out the number of distinct real values for this k such that the system has infinitely many solutions. So now we can say here the value of number of distinct value k can take is 2 from this 0 and 2. Okay, now let's solve question 2. Question 2 says the sum of eigenvalues of a matrix. Here it is very simple question. It can take only few seconds with the help of property. The property say the all the eigenvalues. If I am adding the all eigenvalues for any matrix, here this matrix is 3 cross 3, so it has 3 eigenvalues. Let's call it lambda 1, lambda 2, and lambda 3. And addition of all those eigenvalues, it exactly same as the trace of matrix. Let's call this matrix as A. So I can say the trace of A. Now here the trace of any matrix, it is nothing but just simply the sum of its all diagonal entries. Here the diagonal entries are 1, 5 and 1 respectively. So now add those three numbers. So I can get the trace of matrix A, but it is nothing but just simply 7. So now it is exactly same as the sum of eigenvalue, and what is, and that's what they are asking. So I can say the option B is the sum of all eigenvalue, and which is 7. Now let's move to the next question. Okay, now let's solve question 3. Question 3 says let P and Q be real numbers such that P square plus Q square is equal to 1. The eigenvalues of matrix, we have given a 2 cross 2 matrix in this form of this P Q minus P, and they are asking about the eigenvalues. So here we don't know the value of this variable P and Q here. So just simply we have to use the property of eigenvalues. Basically we need two property. So first property relate the sum of eigenvalue with the trace of any matrix. Here let's call this matrix is again A. I can say the trace of matrix A. And the second property relate the determinant and the multiplication of all eigenvalue. Here the eigenvalues are 2 because the matrix is 2 cross 2. The multiplication of those two eigenvalues is nothing but the determinant of matrix. Here the matrix is A. So now simply we have to use those two property to find the correct set of eigenvalue from this four option. So now let's first of all find the trace of this matrix A here. So now again the trace is nothing but simply the sum of those two diagonal elements. So I can say here the trace is 0 because this plus P and minus P will add and give sum as 0. Now we also need the determinant. So now let's find it here. So I can say the determinant is nothing but here just simply minus p square minus q square. So now I can take minus common from this. So I can say p square plus q square. But now here we don't know the value of this unknown p and q, but we have given a relationship in this form, p square plus q square equal to 1. So let's replace this bracket with 1 from this condition. So I can say the determinant is nothing but simply minus 1. So now let's go through this four option and first find the sum of two numbers and then multiplication and check with which option is give the same result as this 0 and minus 1. So now let's sum those two numbers. So here the trace is 0 and the multiplication is negative 1, which is exactly same as this trace as 0 and the multiplication negative 1. So I can say the option A contains the correct set of eigen values for this matrix here. You can also check for the option C and remaining option. They will not satisfy this both condition. So now let's check for the option B. Option B give the trace as 2 and the multiplication is 1. So now the this both condition is violated in this option B. So I can say option B is not correct set of eigenvalue. Now look at the option C. Option C gives the sum as 0. So this first condition is going to hold for this option C, but the multiplication here is plus 1. So again this second condition is violated in this option C. So option C is also not correct set of eigenvalues. Now let's move to the option D. Again option D give the sum as 0 and the multiplication is non-zero. And here the multiplication is depend on the values of P and Q. Here the multiplication is P square and Q square. So now here we do not have given any condition regarding this P and Q. So we cannot say whether what is the value of this multiplication. So we can also cancel out this option D. So now simply we can say the only option A satisfying those both condition is the correct set of eigenvalues for this 2 cross 2 matrix. Okay, now let's solve question 4. Question 4 says let A be a 10 cross 10 matrix such that A to the 5 power is null matrix and I be the 10 cross 10 identity matrix. The determinant of this A plus I is what? Okay, so first of all we have given a matrix A which is a 10 cross 10 matrix, and further we have given if we take the fifth power of this matrix A, then we are getting as null matrix. Here the null matrix is nothing but its all entries are 0, and here this null matrix is also a 10 cross 10. So now just simply let's represent this null matrix with 0 here. Now this 0 is not scalar but rather it is a null matrix, because on the left hand side we have a matrix, so on the right hand side we must have a matrix. So this 0 represents this null matrix with 10 cross 10 order, and now here this I be the identity matrix, and they are asking about this determinant. So we have to find the determinant of this A plus I, and now again this A plus I is also a 10 cross 10 matrix, because here this matrix A is also 10 cross 10, and here this identity matrix is also 10 cross 10. So the addition of those two matrices is also the 10 cross 10. So now here we have to simply first of all need to find the matrix A. We don't know any entry in the matrix A, but we know the condition A to the 5 equal to null matrix. But now one important property for the eigenvalues, I can write if let's say lambda 1 is eigenvalue of matrix M, sorry matrix A, here we have matrix A is eigenvalue of matrix A, then I can say lambda 1 to the 5 power is eigenvalue of matrix A to the 5. So now here if I replace this A with lambda 1 to the 5, and which is the first eigenvalue, and now here on the right hand side we have a null matrix, and the null matrix has property because its all entries are 0, then we can say any null matrix any null matrix all the eigenvalues of any null matrix are 0. So now it is the property for any null matrix because its all entries are 0. So now if I replace the left hand side with lambda 1 to the 5, then I must have to replace the right hand side with scalar with 0 because the eigenvalue of this null matrix is 0. So now I can say let's call lambda 1 to the 5 on the left hand side, then the right hand side must be 0, and here this 0 is scalar because we have scalar on the left hand side, so we must have scalar on the right hand side. This 0 come from this null matrix because any null matrix has all its eigenvalue as 0. So now I can say the first eigenvalue for this matrix A is 0 from this condition. Now in the same way, let's call lambda 2 is the second eigenvalue for this matrix A, and I can say lambda 2 to the 5 is again equal to 0 because again the second eigenvalue for this null matrix is also 0. So now from this equation I can also say the lambda 2 is also 0. Now in the same way I can go lambda 10 because the matrix A is 10 cross 10, so it has 10 eigenvalues. So lambda 10 to the 5 is again 0. So again I can equate this lambda 10 equal to 0. So we can say the all eigenvalues of this matrix A are 0, or in the other word we can say the option, sorry, this matrix A is nothing but the null matrix because the all eigen for any matrix, if its all eigenvalues are 0, then the matrix must be null matrix because the only the null matrix is the matrix which has all eigenvalues as 0. So now we can say here this matrix A is null matrix. So now this matrix A is disappear from this determinant because it has all entries as 0. So I can say the determinant of this A plus I is nothing but just simply the determinant of I matrix, and here the I is 10 cross 10. So now the determinant of any identity matrix is just simply 1. So now we have find out the determinant. You can also go by finding the eigenvalues of this A plus I matrix. We know if the lambda 1 is the eigenvalue for this matrix A, then the eigenvalue of this A plus I nothing but the lambda 1 plus 1 because this identity matrix, we can say for any identity matrix its all eigenvalues are nothing but just simply 1. So now if we know the eigenvalues of this matrix A, then we can easily find the eigenvalue of this matrix. So now let's do it here. If I am interested in the finding the eigenvalue of this A plus I matrix, so now let's call it beta 1, and which is corresponding to lambda 1. So now just simply replace this A with this first eigenvalue which is 0. So I can say 0 plus, and now replace this I with 1 because any identity matrix has all its eigenvalue as 1. So I can replace this I with 1. So the value of beta 1 is 1. In the same way I can say the second eigenvalue for this matrix, let's call it beta 2, is again replace this A with second eigenvalue, in this case here 0, and replace this identity with 1. So I can say the second eigenvalue for this A plus I matrix is nothing again 1. In the same way I can go up to beta 10. So now select this lambda 10 for this A. So I can say 0. The same way again replace this identity matrix with unity. So again the eigenvalue is 1. Now with the help of property I can say the determinant of this A plus I is nothing but the multiplication of all its eigenvalue, and here the eigenvalues are beta 1, beta 2 and up to beta 10, and here all those entries are 1. So I can say the determinant of this A plus I here is nothing but just 1. So now we have find out the determinant of this A plus I, and it is 1. Okay, now let's move on the next question. Question 5 is consider a n cross n matrix A. Okay, we have given a matrix A which is n cross n matrix, and a non-zero n cross 1 vector P. We have a vector P which is n cross 1. Their product, we have given the product in this form: A multiplied with P is equal to alpha square times P, and here where alpha belongs to R and alpha does not belong to this vector, it means alpha does not belong to any kind of vector, it is only a scalar and it belongs to the R. Based on the given information, the eigenvalue of S square is what? Okay, so they are asking about the eigenvalue of a square. So now to find the eigenvalue of a square, first of all we need the eigenvalues of a. Once we know the eigenvalues of a, then we simply square it and we get the eigenvalue of this a square matrix, because we know from the property if lambda 1 is eigenvalue of matrix M, then lambda 1 to the n power is eigenvalue of this matrix to the n power M to the n power matrix. It is a basic property that eigenvalue has. If the lambda 1 is the eigenvalue of any matrix, then lambda to the n power, it is nothing but the eigenvalue of this initial matrix to the power n. Now to find the eigenvalue of this m square, first of all we need the eigenvalue of this matrix A. So now here compare this equation AP equal to alpha square time P equal to AX equal to lambda x. You can see here this P is nothing but the vector. Here it's given this P is n cross 1 vector. So now you can see this vector is exactly repeating on the right hand side also, and here this A is nothing but the matrix. So now let's compare this equation with this AX, our general equation AX equal to lambda x. Now here this x is a vector. Now here this x is replaced with P, and here this matrix A is any general matrix. So now we can compare this alpha square equal with this scalar, and here this scalar is nothing but the eigenvalue for this matrix A. So now here we can say one of the eigenvalue for this matrix A, let's call it lambda 1. It is nothing but this, just simply this scalar. And here this scalar is alpha square. So we can say one of the eigenvalue for this matrix A is alpha square, and when we need the eigenvalue of A square, so just simply square it. So I can say lambda 1 square is the eigenvalue of this matrix A square. So I can say simply alpha to the 4th power, it is the one of the eigenvalue for this A square matrix. Now option B is the correct one about the eigenvalue of this A square matrix. Now let's move to the question 6. Okay, now let's solve question 6. Question 6 says if we have matrix P which is a 2 cross 2 and matrix Q which is also again a 2 cross 2, then they're asking about the multiplication of Q transpose times P transpose. So now this question can be solved in the two way. If you directly find the transpose and directly multiply the two matrices after taking the transpose, and the second way is this, first multiply those P and Q and then take transpose, because we know if we have this matrix PQ and if we take the transpose, and if we want to apply the transpose operation to individual to this matrices, then we have to reverse the order. So I can say P transpose times Q transpose is exactly same as the transpose of this multiplication. So now here I can say this Q transpose multiplied with P transpose, it is nothing but the multiplication of PQ and then take the transpose. If you do the same thing that we have did with this first equation, so you can say it is exactly Q transpose times P transpose, and that's value we have to find out. So you can simply multiply those P and Q matrices, and after multiplication simply take its transpose. So now let's do it here. Let's find the PQ matrix. So now here the matrix P is nothing but 1, 2, 3, 4, and the matrix Q has a value 0, 1, 1, 0. So now let's find the resultant matrix after the multiplication. So here this first entry will be 2, the second entry here is 1, here this entry will be 4, and this entry will be 3. And now to reach our final answer, we have to take the transpose of this PQ. So I can say PQ transpose. So I have to take the transpose of this 2 cross 2 matrix. Simply reverse this rows and column. So now it is our resultant matrix. So I can say here option D, not option B. So I can say this is our resultant matrix for this multiplication of Q transpose and P transpose. So I can say option D is the correct one. You can also get the same answer if you take the transpose of this matrix Q and then multiply. Let's quickly do it here. So here we have to first take the Q transpose. So now the transpose of this matrix will be this one, and now we have to multiply this Q transpose with P transpose. So now let take the transpose of this P. So this first row, so this first row will be our first column after taking the transpose, and this second row will be our second column. So now again let's find the resultant matrix after multiplication. So here this entry will be 2, here this will be plus 4, and here this will be 1, and this entry will be 3. So you can see the same matrix as we got in the first case. Now let's move to the next question. Okay, question 7 says the rank of matrix. They are asking about the rank of this matrix. Here the matrix is 4 cross 4. So now from the basic concept I can say the rank of this matrix, let's call it A. The rank of A, it must be less than or equal to 4, because it cannot have rank more than 4. So it must have rank either exactly 4 or less than 4. So now to find the rank of this matrix we have to reduce this matrix into echelon form. So first of all let write this matrix as it is here. Second row is 3 4 2 5. The third one is 5 6 2 7, and the last one is 7 8 2 9. Now for now to find the rank of this matrix we need this matrix into echelon form. So now we need this entry as 0, this entry as 0, and this entry as 0 into the echelon form. So now to make all those three entries as 0 we have to perform some row operation. So now I can write, if I subtract the third times 3 times this first row with second row, so this element will be 0, and if I subtract 5 times this first row from this third row, so this element will also 0, and if I subtract this first row with 7 times from this last row, so this element is also 0. So now let's write it here in this equation form. So I can say row 2 minus 3 times row 1, it will give me new row 2. In the same way I can say row 3 minus 5 times row 1, it will give me new row 3. In the same way row 4 minus 7 times row 1, it will give me new row 4. So now after those 4 operations what we are getting, let's put it here. So the first row will remain as it is 2 2 3. So now our second row here, this entry will be 0. So now here this 2 is multiplied with negative 3, so it will be negative 6. We have already plus 4, so we are getting negative 2. Here also negative 6, we have already plus 2, so I can say negative 4. And here this 3 multiplied with negative 3, so negative 9. We have already plus 5, so again negative 4 is there. Now for the third row, here this entry is also going to 0. And now here negative 10 plus 4, so negative 4. And here again negative 10, we have already plus 2, so negative 8 there. And here also we have to multiply this 3 with negative 5, so I can say negative 15. We have already plus 7, so I can say negative 8 again. Now in the last row this entry is again going to 0, because we are multiplying this first row with negative 7 and adding in this third one. So this entry will be negative 14. We have already plus 8, so I can say negative 6 is there, and we have to again multiply these 2 with negative 7, so again negative 14. We have already plus 2, so negative 12 is there. The same way here we are getting negative 21. We have already plus 9, so again negative 12 is there. So now you can easily see here this third row and fourth row is nothing but the twice as twice much as the second row for this third row, and the this last row is 3 times this row second row. If you multiply this row second row with 3, then this entry will be 6, here minus 12, here minus 12, which is exactly identical as this third row. And if you multiply this second row with negative 2, sorry, plus 2, then you are getting here negative 4, negative 8, negative 8, which is exactly same as this second row. So now to reduce further this matrix, you can perform two more row operation, and which are just simply if you subtract 2 times row 2 from row 3, it will give you new row 3, and if you subtract 3 times row 2 from row 4, and it will give you new row 4. So simply you reduce this two row all as a 0 0, because those two rows are linearly dependent on this second one. So we can say the rank of here this matrix is 2, because we are getting two non-zero rows, this first row and this second row are only the two non-zero rows, or in the other word we can say the matrix has two linearly independent rows, because after doing those those two operations we are getting resultant matrix like this. Let's put it here. This first row will remain as it is, this second row is also remain as it is, and now the this last two row will be in this 0 0 form. So now you can easily see the rank of this matrix is nothing but the number of non-zero rows. Here the number of non-zero rows are 2. So the rank is 2 for this matrix. So we can say the option A is the correct in this question. Now let's move to the question 8. Question 8 says the smallest eigenvalue and corresponding eigenvectors of matrix. We have a 2 cross 2 matrix respectively are, okay, they are asking about the smallest eigenvalue and the corresponding eigenvector. Now this word is important here, corresponding, because the eigenvector it must be correspond to this minimum eigenvalue. So now this matrix is 2 cross 2, so it has two eigenvalue. We have to select the smallest one and we have to find the corresponding eigenvector for the smallest eigenvalue for this matrix. Now to find the eigenvalues for this matrix, we necessarily first make the characteristic equation, and from that characteristic equation we can find the root of this dot this that equation. So now simply we have to, let's call again this matrix as A. Simply the A minus lambda I, and we have to equate this determinant equal to 0 to find the characteristic equation. So now here I can say 2 minus lambda minus 2 minus 1 6 minus lambda, and let equate this determinant equal to 0. So simply now find the determinant. Here I can say 6 minus lambda, sorry, we have negative 2 here, and we have to equate equal to 0. So now let's do the multiplication for those two brackets. So now here 12 minus 8 lambda plus lambda square minus 2 equal to 0. So I can say lambda square minus 8 plus 10 equal to 0. So now it is a quadratic equation in this form of lambda square. So now we need the root of this equation. So simply use this formula for the finding the root of any quadratic equation. B plus or minus under root of delta. Here delta is nothing but simply b square minus 4ac by 2 times a. Here this a is the coefficient of this lambda square term and b is the coefficient of lambda. Here we are getting minus 8 lambda. I missed here lambda, so minus 8 lambda. So now, and now here this c is nothing but this constant term. So simply put all the values here. So I can say plus 8 plus or minus under root of 64 minus 40, because 4 times this 10 will be 40 divided by 2. So let's simplify further. So I can say 8 plus or minus under root of 24, 64 minus 40 will be 24 divided by 2. So now let's find the two roots. One time take plus sign and one time take negative. So I can say So the first root is 6.44. So it is the first root. Now the second root will be 8 minus under root of 24 divided by 2, and it is 1.55. 1.55. So now we have find out the two eigenvalue for this matrix A here, and which are 6.44 and 1.55. So now they are asking about the smallest eigenvalue. So now this one is the smallest eigenvalue. So I can say the smallest eigenvalue for this matrix A is 1.55. So let's look at the option. So you can only cancel this option C because it has eigenvalue as 2, and but we are getting the eigenvalue as 1.55. So the remaining option, this A, B and D, has the eigenvalue as this 1.55. So now we have to move to the corresponding eigenvector concept. And now for the finding the corresponding eigenvector, one can find with the conventional method with the help of this lambda, this ax equal to lambda x. But now here we have given the vector in the option, so simply use this concept ax equal to lambda x. So now here we already have a matrix A. So now let's put it here: 2 minus 2 minus 1 6. Now let's start with the option A. So option A has vector 2 comma 0.45. So now let's find the multiplication. So now here these 2 multiplied with plus 2, so 4 minus 2 multiplied with 0.45. So here the first entry is 3.1. Now the second entry will be minus 2 plus 6 times 0.45, so it will give 0.7. So now we have to represent this matrix into this lambda time initial one, and here the initial vector is this 2 comma 0.45. But now here this scalar is fixed, and which is this 1.55, and then the corresponding then we find the corresponding eigenvector, and in the question it is given that the eigenvector is corresponding to this minimum eigenvalues. So now the minimum eigenvalue is this 1.55. So now this scalar it must be 1.55. So now if you find here this scalar, so I can say 3.1 is nothing but this lambda time 2 from this first entry the left hand side and right hand side. So now I can say here the scalar is 3.1 divided by 2, and it is 1.55. So yes, it is the exactly same as this one. You can also check for this last entry. If you multiply this 0.45 with 1.55, so you will get 0.7. So I can say this condition is going to hold if this scalar lambda take the value as 1.55, and which is the minimum eigenvalue for this matrix A. In the other word, I can say the option A is the correct set of eigenvalue and corresponding eigenvector for this 2 cross 2 matrix. So option A is the correct option. You can also check for this vector and this vector. They will not give this scalar as this 1.55. So those vectors are not the correct eigenvector. They have given the correct eigenvalue but not the correct eigenvector corresponding to this eigenvalue. So the only option A is the correct one. Okay, now let's solve question 9. Question 9 says if A is a square matrix. Okay, we have given a matrix A which is a square matrix. Let's assume any n cross n square matrix, then orthogonality property maintenance. Okay, so they're asking about the orthogonality property. So now if any matrix is orthogonal, then it has very basic this relationship. If I multiply any matrix with its transpose, and after multiplication I am getting the identity matrix in the output of this multiplication, then I can say here the matrix A here, matrix A is orthogonal. So now if this is going to happen, then I can say here this matrix is orthogonal. So now the option B correctly give this condition A times A transpose, or I can in the other word I can also reverse this order A transpose times A. It is also the identity matrix. It is also the condition for the orthogonality of any matrix. So now the only option B gives this condition. So option B is the correct relationship regarding this orthogonality property of matrix. Okay, now let's solve last question for this video. Question 10. Question 10 says given a matrix we have a matrix which is again 2 cross 2 matrix. The value of determinant. So they are asking about the determinant of this matrix which is formed with the help of this A in some polynomial form. So now to find the determinant of this matrix we have to use the concept of eigenvalue. So now first of all we know the multiplication of all eigenvalue of any particular matrix is nothing but the determinant of what of this particular matrix. But now here we don't know the eigenvalue of this matrix. This one represents as a whole matrix. But we can find the eigenvalue of this matrix A easily because it is a 2 cross 2. And further look at this matrix. It is nothing but the triangle matrix. See here. So I can say here A is upper triangular matrix. A is upper triangular matrix. Whenever any matrix is either the upper triangular or lower triangular, it has one property that its all eigenvalues are nothing but simply its all diagonal entries. The diagonal entries here is 2 and 3. So I can say the eigenvalue for this matrix A, let's call its lambda 1 is 2, and the second eigenvalue, let's call its lambda 2 is 3. So now we have find out the eigenvalue of this matrix A easily with the help of property of this triangular matrix. So now to find the determinant of this matrix, we also need the eigenvalue of this matrix. Once we have find out the eigenvalue, simply we have to multiply those two eigenvalue and we can equate the multiplication equal to the determinant of this matrix. So now let's call it lambda 1 prime and lambda 2 prime, and it is the multiplication of those two number. It is nothing but the the determinant of this matrix. Let's call this matrix as B as whole to simply write here. So now here this matrix B has some particular relationship with matrix A in this polynomial form. So now the another property is that if we make any matrix with the help of the initial matrix A in this some polynomial form, then the resultant eigenvalue of the resultant matrix, it is nothing but the same polynomial function is performed on the individual eigenvalue to find the individual corresponding eigenvalue of the new matrix. So now here I can say let's find this lambda 1 prime for this matrix B. So now I can say lambda 1 prime, it is nothing, just simply replace this A here with this first value because we are finding the first eigenvalue for this B matrix, and now replace this I with 1 because we know any identity matrix has all entries are 0 except its diagonal entries. So now if you find the characteristic equation of any identity matrix and you will find the root of that particular characteristic equation, it nothing but simply 1. So I can say all the eigenvalues of any identity matrix is 1. So now replace this A with 2. So I can say here 2 to the 4th power minus 5 times 2 to the 3 plus 6 times 2 square plus 2 times 1. So now let's simplify it. So I can say here 16 minus 5 multiplied with 8. Here this 6 multiplied with 4 and here 2. So now if you simplify it algebraically, so you end with plus 2, and which is the first eigenvalue for this matrix B. So now in the same way I can also get the second eigenvalue. Let's call it lambda 2 prime because we have given here name. So simply now this time replace this A with this 3 because we are finding the second eigenvalue. So I can say here 3 to the 4th minus 5 times 27 plus 6 times 9 plus 2 times again 1. So now you can further algebraically simplify it. So now if you do the simplification, again you will get 2, and it is the second eigenvalue for this matrix. So now we have find out the two eigenvalues for this matrix. Now here this matrix is also 2 cross 2 because here the matrix is 2 cross 2. So this B matrix is also 2 cross 2. So it must have two eigenvalues, and which are this plus 2 and again plus 2. So now simply we need the multiplication of those two numbers. So I can say 2 multiply with 2, and it is the determinant of this matrix B, and here this matrix B is nothing but this matrix, and so I can say the determinant is 4. So now let's put 4 here, and which is the determinant of this matrix. And thanks for watching this video. See you later on the next video. Till then, bye bye.